Right now, 2.5 million light years from where you are sitting, there is a galaxy with 1 trillion stars, and it is falling toward us at 110 kilometers per second. It is approaching. It is closing. It is, by the standards of cosmic motion, moving fast. The galaxy is called Andromeda. The Greek-derived name refers to a constellation in the northern sky, named in turn for the daughter of an ancient queen. In the modern catalogue, the galaxy bears the designation MNRAS 1. It is the largest galaxy visible to the naked eye when conditions are right. From a dark site on a moonless night, you can see it as a faint smear of light slightly larger than the full moon, hanging in the autumn sky. The smear is in fact much larger than the moon. The angular size of Andromeda on our sky is roughly 6 times the angular size of the full moon. But the surface brightness is low. Most of the light is too faint to register on the unaided eye. What we see with our naked eyes is only the brightest central region. The full extent of the galaxy stretches across a span of sky that would, if our eyes could detect it, be quite large. What is closer to us than Andromeda? Almost nothing of significant size. The Magellanic Clouds, 2 small irregular satellite galaxies of our own Milky Way, are closer. The smaller galaxies of the local group are mostly closer. But of the major spiral galaxies, the kinds of galaxies that look like our own, Andromeda is the nearest neighbour. Tonight we're going to walk through what that proximity means. You do not need to hold every number. Some you will. That is enough. Andromeda is not threatening, in any urgent sense. The events we are about to discuss unfold over billions of years. We have time. The galaxy approaching us is on a long, quiet trajectory. We have a couple of hours. If you have come here to rest, let this carry you. The galaxy approaching us is on a long, quiet trajectory. Nothing happens for billions of years. We sit in the meantime, in the early evening of a vast, cosmological story. Now let us pull back. Let us look at how we came to know that Andromeda is what it is, and how we came to know that it is approaching. The story begins in the modern era, in 1923. In that year, on the night of October 5th, an astronomer at Mount Wilson Observatory in California pointed a 100-inch telescope at the soft glow in the constellation of Andromeda. The astronomer's name was Edwin Hubble. The telescope was, at the time, the largest in the world. What Hubble was hunting for was, in technical terms, a particular kind of variable star. The kind he wanted to find was called a Cepheid. Cepheids are stars whose brightness varies in a regular periodic pattern. The period of the variation is tightly linked to the intrinsic brightness of the star. If you can measure the period and the apparent brightness, you can derive the distance. Hubble had been working on the M31 Nebula, as it was then called, for some time. The question he was trying to answer was profound. Was M31 part of our own Milky Way galaxy, a relatively nearby cloud of stars and gas, or was it something much farther away, a separate galaxy of its own? The question, in 1923, was one of the most contested in astronomy. Some astronomers, led by Harlow Shapley at Harvard, argued that M31 was inside the Milky Way. Others, including Haber Curtis at Lick Observatory, argued that M31 was an external system. The matter had been debated, formally, in what became known as the Great Debate of 1920. The Great Debate had not resolved the question. The debate had simply made the question clearer. The crucial missing piece was a reliable distance measurement. Without that, the arguments on either side were based on indirect evidence. Hubble had the instrument. He had the technique. On the night of October 5th, he took a long exposure of the M31 Nebula. The image was developed in the observatory darkroom and examined under careful lamps. He found a star. The star was on the outskirts of the bright central region of M31. The star was faint, magnitude 18.2. By measuring this star against earlier exposures of the same region, Hubble determined that the star was varying in brightness. The period of variation was approximately 31 days. A 31-day Cepheid in our galaxy would be intrinsically bright. The relationship between period and brightness, known as the Leavitt law, after the astronomer who established it, gave Hubble the intrinsic brightness. Combined with the apparent brightness measured on the plate, the distance came out at roughly 1 million light-years. 1 million light-years. The number was, at the time, the largest distance ever determined for any object. It placed M31 firmly outside our own Milky Way. The great debate was settled in favour of Curtis. M31 was an external galaxy. The universe we now understood contained many such galaxies. The Milky Way was one of many. Hubble's measurement was, in retrospect, slightly low. The correct distance, as we now know, is approximately 2.5 million light-years. The factor of 2 error came from confusion between different types of Cepheid variables. The error was corrected in the 1950s, when the Cepheid period-luminosity relation was recalibrated. But the qualitative result stood. M31 was an external galaxy. The universe was a vast collection of such systems. Our Milky Way was one among many. The geocentric model of the cosmos had been definitively replaced by a model of countless galaxies, scattered through unimaginable distances. This was, in some sense, one of the greatest expansions of the human conception of the cosmos. In a single careful exposure, a single careful star measurement, the size of the known universe had grown by a factor of 100 or more. Now let us pull back, fellow night watcher. I want to spend some time on what M31 actually is, given what we now know, because the picture has refined enormously since Hubble's original measurement. M31 is a spiral galaxy. Like our own Milky Way, it consists of a flat, rotating disk of stars and gas, with spiral arms winding outward from a central bulge. The disk is much larger than the disk of the Milky Way. M31 is approximately 220,000 light-years across, more than twice the diameter of our own galaxy. The mass of M31 is also greater than that of the Milky Way. The best current estimates put M31 at roughly 1.5 trillion solar masses, including dark matter. The Milky Way is roughly 1 to 1.5 trillion solar masses, somewhat less than M31. The two galaxies are comparable in mass, but M31 is the heavier of the two. The number of stars in M31 is approximately 1 trillion. The Milky Way has approximately 250 billion. M31 in this measure has roughly 4 times as many stars. M31 contains, like the Milky Way, a central supermassive black hole. The black hole at the centre of M31 has a mass of approximately 150 million solar masses. The black hole at the centre of the Milky Way, Sagittarius A star, has a mass of approximately 4.3 million. The M31 central hole is roughly 35 times more massive than ours. The two galaxies are in many ways twins. Two large spiral galaxies comparable in size and mass, separated by a distance that, by cosmic standards, is small. The distance, as I mentioned, is 2.5 million light-years. That number deserves to be held for a moment. 2.5 million light-years. In light travel terms, that is the time it took the light we now see from M31 to reach us. The light left M31 2.5 million years ago. It has been crossing the space between us at the speed of light for that entire duration. When the light left M31, the Earth had different inhabitants. The first stone tools were being made by early hominins on the African plains. The continents were in their present configuration. But the climate was different. There were no humans of our species. The biosphere was, in many ways, unrecognizable. The light has been traveling continuously ever since, through interstellar gas, through the magnetic fields of the intergalactic medium, through the slow expansion of cosmic space. The light has been on its solitary journey, untouched for the entire span of human prehistory. The light arrives now. We see what M31 looked like 2.5 million years ago. That distance, 2.5 million light-years, is, by cosmic standards, small. Let me bring that closer. The diameter of the Milky Way is roughly 105,000 light-years. The distance to M31 is 24 times the diameter of our galaxy. If you imagine the Milky Way as a disk 1 inch across, M31 sits at a distance of about 2 feet. That is close. By cosmic standards, that is very close. The local group, the gravitationally bound system that contains the Milky Way, M31, and roughly 80 smaller galaxies, spans about 5 to 10 million light-years. The two major galaxies, the Milky Way and M31, are the gravitational anchors of the system. The smaller galaxies are mostly satellites of one or the other. We are bound together. M31 and the Milky Way are not just passing in the night, they are gravitationally locked. Whatever happens in the local group over the next 10 billion years will involve primarily the two of us. This is the situation. Two large galaxies, comparable in mass, separated by a distance that, gravitationally, is intimate. Let me hold what gravitational intimacy means in this context. Galaxies, as I have walked through, are not solid bodies. They are diffuse extended systems, gravitationally bound but not rigidly connected. The intimate distance in gravitational terms means that the gravitational pull of each galaxy on the other is substantial enough to determine the long-term dynamics. If M31 and the Milky Way were 10 times farther apart, the gravitational pull would be 1/100th as strong. The two galaxies would still attract each other, but the attraction would be too weak to overcome the cosmic expansion. The galaxies would, on cosmic timescales, drift apart rather than fall together. If M31 and the Milky Way were 100 times farther apart, the cosmic expansion would dominate completely. The galaxies would drift apart at roughly the Hubble flow rate. There would be no future merger. The two galaxies would simply move further apart indefinitely. But we are at the actual distance, 2.5 million light-years. At this distance, the gravity wins. The cosmic expansion is overcome. The galaxies fall toward each other. This is the test of gravitational binding. The two galaxies are inside the gravitational potential well that contains them both. The well is deep enough that no internal dynamics can throw either galaxy out. The two galaxies are stuck together, in the sense that gravity ensures they will eventually meet. The meeting takes time. Gravitational dynamics, at the scale of galaxies, is slow. The two galaxies have been falling toward each other for many billions of years. They will continue to fall for another 4.5 billion years before the first close passage. The dynamics are inexorable. This is what gravitational intimacy looks like at the scale of galaxies. Slow, inexorable, unavoidable. What happens next is set by the dynamics. Now let me bring this closer. I want to walk through what we know about the motion of M31 toward us. The radial velocity, the component of motion along our line of sight, has been known for over a century. Vesto Slipher at Lowell Observatory in Flagstaff, Arizona, measured the spectrum of M31 in 1912. The spectral lines were shifted toward the blue end of the spectrum. The blue shift indicated approach. The magnitude of the shift, when interpreted as a Doppler effect, gave a radial velocity of approximately 300 kilometers per second toward us. This was, at the time, a surprising result. Most galaxies were observed to be moving away from us, with redshifted spectra. M31, by contrast, was approaching. The result was one of the early hints that the cosmic motion of galaxies was complex, that not everything was simply receding. The radial velocity has been refined many times since Slipher's original measurement. The current best value, corrected for the Sun's motion within the Milky Way, is approximately 110 kilometers per second. M31 is approaching the Milky Way at roughly 110 kilometers per second, along the line connecting our two galaxies. That is the radial component. The tangential component, the motion perpendicular to our line of sight, was harder to measure. For most of the 20th century, the tangential component of M31's motion was unknown. We knew it was approaching us, but we did not know whether the approach was direct or whether M31 had a significant sideways component. The breakthrough came in 2012. A team led by Sangmo Sohn at the Space Telescope Science Institute used decades of Hubble Space Telescope imaging to measure the actual motion of M31 against the background of distant galaxies. The technique requires extremely precise positional measurements. The motion is small. The displacement of M31 against the background over decades of observation is only fractions of a millisecond per year. But the Hubble Space Telescope, with its stable optics and long-duration imaging, can measure this. The result, when worked through, was that M31's tangential velocity is approximately 32 kilometers per second. The motion is mostly toward us. M31 is heading roughly straight at the Milky Way. The combined velocity, accounting for both the radial and tangential components, places M31 on a collision trajectory. The two galaxies are heading toward a close encounter. Let me hold the Sohn measurement for a moment, because it required extraordinary precision. The Hubble Space Telescope, in operation since 1990, has been imaging M31 for decades. The imaging programs were originally designed for various scientific purposes, but the images also serve as astrometric records. Each image preserves the precise positions of stars and other features on the sky. By comparing images taken many years apart, astronomers can detect the small displacements of objects on the sky. For nearby objects, the displacements are large. For distant objects, they are tiny. M31, at 2.5 million light-years, moves very slowly across our sky. The expected angular motion, given the radial and tangential velocities, is approximately 20 millionths of an arcsecond per year. An arcsecond is 1/3/600th of a degree. 20 millionths of an arcsecond is, in standard human terms, an unimaginably small quantity. Detecting this motion requires extraordinary precision. The Hubble Space Telescope, with its stable optics in orbit above the atmosphere, can achieve such precision over long baselines of time. The technique involves measuring the positions of bright stars in M31 against the background of distant quasars and other galaxies. The distant background objects being so far away do not appear to move. The M31 stars against this stationary background can be tracked. Sohn and colleagues used images of M31 taken over a period of several years. They measured the average motion of many stars within M31 relative to the background. The cumulative result, after careful statistical analysis, was the tangential velocity I have quoted. The measurement was, in some sense, a triumph of precision astrometry. It required years of careful data accumulation. It required sophisticated analysis to extract the small signal from the noise. It required calibration against the stable background of distant objects. The result, when published in 2012, was a milestone. For the first time, we had a measurement of M31's complete three-dimensional motion. The future trajectory could be computed with much higher confidence than before. The merger prediction was, in some sense, made quantitative. The Sohn measurement was refined in 2021 using data from the Gaia satellite. Gaia's astrometric mission, which measures the positions and motions of stars across the sky, can be applied to bright stars in M31 to measure the galaxy's overall motion with even higher precision. The Gaia result is broadly consistent with Sohn's, though it suggests a slightly larger tangential velocity, perhaps in the range of 39 to 45 kilometers per second. Either way, the picture is clear. M31 is on a collision trajectory with us. The collision is not immediate. The collision unfolds over billions of years. But it is, by current best models, inevitable. Stay with me here. Let me hold the implications of the radial velocity measurement first. Slipher's measurement, in 1912, was one of the early triumphs of stellar spectroscopy applied to galaxies. The technique involved obtaining a spectrum of M31, identifying the absorption lines of various elements in the spectrum, and comparing them to the laboratory reference wavelengths. The lines in M31's spectrum were shifted from their laboratory wavelengths. The shift was, in absolute terms, small, but it was measurable. The direction of the shift was towards shorter wavelengths, the blue end of the spectrum. The shift, interpreted as a Doppler effect from the motion of M31 relative to us, indicated approach. The magnitude of the shift when converted to velocity was approximately 300 kilometers per second. The number was large by the standards of stellar motions within the Milky Way. It was, in some sense, surprising. Most galaxies had subsequently turned out to be moving away, redshifted by the cosmic expansion. M31 was a notable exception. The number has been refined over the past century. The current best value, corrected for the Sun's motion within our galaxy, and various other systematic effects, is approximately 110 kilometers per second. The radial component of M31's motion toward us has been measured with increasing precision over decades of work. The result is solid. M31 is approaching us in the radial direction at approximately 110 kilometers per second. The approach is real. The approach has been continuing for at least the duration of human astronomical observation, and presumably for much longer. When two galaxies of the size of M31 and the Milky Way approach each other on a collision trajectory, the resulting interaction is not a simple impact. Galaxies are not solid bodies. They are diffuse collections of stars, gas, and dark matter, held together by gravity. When two galaxies come together, the dominant interaction is gravitational, not collisional. The first close passage, expected in approximately 4.5 billion years, will bring M31 and the Milky Way within roughly 100,000 light-years of each other. At that distance, the gravitational pull of each galaxy will distort the structure of the other. Spiral arms will be pulled out into long tidal streams. Star formation will be triggered in the compressed gas regions. The galaxies will look from outside like two soft luminous shapes interpenetrating each other. The first passage is, by the simulations, not a permanent merger. The galaxies will pass through each other, fly apart, and then fall back together for a second close passage about 1 billion years later. After 2 or 3 such passages, the galaxies will have lost enough energy to gravitational tidal effects that they will settle into a single, merged object. The final merger product predicted by simulations is a single large elliptical galaxy. The disk structure of the original spirals is destroyed in the merger process. The stars from both galaxies are mixed into a more spheroidal distribution. The new object has no rotating disk. It has instead a roughly spherical body, with stars orbiting in random orientations. Astronomers, with their characteristic dry humour, have proposed naming the result Milkomeda or Milkdromeda. The names combine Milky Way and Andromeda in obvious ways. Neither name is official. The full merger, by current best estimates, completes in approximately 6 to 7 billion years from now. Let me hold that timeline for a moment. 4.5 billion years to the first close passage. 6 to 7 billion years to the complete merger. For context, the age of the Earth is 4.5 billion years. The current age of the solar system is roughly equal to the time until the first close passage. The Sun, our particular star, has been fusing hydrogen for the past 4.5 billion years. It will continue to fuse hydrogen for approximately another 5 billion years. After that, the Sun will exhaust its core hydrogen. The Sun will then expand into a red giant phase. The red giant phase will last approximately 1 billion years. During that phase, the Sun's outer layers will engulf the inner planets, including Mercury, Venus, and very likely Earth. By the time the merger of M31 and the Milky Way is complete, in 7 billion years, our Sun will have already become a red giant. Earth will likely have been destroyed. The biosphere, if any remnant remains, will have ceased. The timeline of the merger and the timeline of the Sun's evolution are, in this sense, intertwined. The galaxy will merge. The Sun will expand. Both events will occur in the same broad cosmic epoch. What this means is that the merger is not a threat to Earth in any urgent sense. The merger is a slow process that unfolds long after the Earth, as a habitable planet, has ceased to exist. The merger is in some sense a cosmic event that occurs in the post-Earth era. This is, I want to emphasize, not a near-term concern. The merger is real, and it is inevitable, but it is in the deep future. Many things will happen, on cosmic and biological timescales, before the merger arrives. Now let me bring that closer. I want to walk through what the merger will actually look like, in terms of what happens to individual stars. Galaxies, as I mentioned, are not solid bodies. The stars within them are widely separated. The typical distance between stars in the disk of the Milky Way is roughly 4 to 5 light years. That is enormous. A light year is the distance light travels in a year. Light travelling at 300,000 kilometers per second covers approximately 9.5 trillion kilometers in a year. 4 light years is roughly 40 trillion kilometers. For comparison, the diameter of the Sun is roughly 1.5 million kilometers. The distance between stars in the Milky Way is approximately 25 million times the diameter of the Sun. When 2 galaxies merge, the stars within them do not, in any meaningful sense, collide. The probability of 2 individual stars approaching close enough to be disrupted by each other is, by careful calculation, extremely low. Most stars never come within billions of kilometers of another. The disk of the Milky Way will pass through the disk of M31 with very few actual stellar interactions. What does happen during the merger is large-scale gravitational rearrangement. Stars are pulled out of their original orbits. New orbits form, often eccentric, often inclined to the original disk planes. Over millions of years, the stars settle into the new gravitational configuration of the merger product. The settling after several close passages and gravitational interactions produces the spheroidal distribution characteristic of an elliptical galaxy. This rearrangement is, from the perspective of any individual star, slow. A star's orbital period in a galaxy is typically hundreds of millions of years. The merger process unfolds over billions. Each star, over its individual experience, undergoes a gradual change of orbital parameters. There is no sudden event. There is no catastrophic interaction. There is only a slow rearrangement. Let me hold the stellar density question for a moment, because it is one of the most important aspects of why mergers do not destroy stars. The disk of the Milky Way has a stellar density that varies with position. Near the center of the galaxy, the density is high. There are tens of thousands of stars per cubic light year. Near the outer edge of the disk, the density drops to perhaps 1 star per cubic light year. In the halo, even less. Even at the highest densities near the galactic center, the stars are still separated by distances that are vastly greater than their own diameters. A typical star, like the Sun, has a diameter of roughly 1.5 million kilometers. The nearest star to the Sun, Proxima Centauri, is at a distance of 4.2 light years, or roughly 40 trillion kilometers. The ratio is about 27 million. When two galaxies merge, the density of stars temporarily doubles in the regions where the two disks overlap. The stellar density goes from roughly 1 star per cubic light year to roughly 2. The mean spacing between stars decreases from 4 light years to perhaps 3. This is still a vast distance. The probability that any individual star will pass within 1 billion kilometers of another star during the merger is, by careful calculation, roughly 1 in a million. Even at the elevated densities during merger, stars almost never come close enough to disrupt each other. The probability of two stars actually colliding, in the sense of physical contact between their surfaces, is essentially zero. The stars are far too small, relative to their typical separations, for actual collisions to occur in any practical numbers, so the merger preserves nearly all the stars. The stars rearrange their orbits but continue their individual lives. Each star's interior physics, the fusion in the core, the convection in the envelope, the magnetic fields, the rotation, continues unaffected. This is why the merger is not a threat to any particular star, including our Sun. The stars survive, the orbits change, the galactic structure transforms. But the individual stars carry on. For our own Sun, the rearrangement during the merger will likely move it to a different position in the resulting galaxy. The Sun's current location in the Milky Way is roughly 2/3 of the way out from the center, in the disk. After the merger, the Sun could be anywhere from close to the center to far in the outer halo. The simulations suggest that the most likely outcome is that the Sun will be migrated outward, ending up in a relatively low-density region of the merger product. But, again, this is not a near-term concern for the Earth. By the time the merger is well underway, the Sun has already become a red giant. The Earth has already been engulfed or, at minimum, scorched into a sterile rock. The biosphere is no longer. The Sun, as a stellar object, will continue. It will eventually shed its outer layers and contract into a white dwarf. It will, in time, cool and fade. None of this depends on the merger. The Sun's life cycle is set by its mass and its initial composition, not by its gravitational environment. The merger will move the Sun. It will not affect the Sun's evolution. Now, stay with me here. This is a subtle point. The Sun is unaffected by the merger in any direct sense. The merger affects the gravitational environment in which the Sun moves, but not the Sun itself. The Sun continues its evolution regardless. This is a general feature of galaxy mergers. The galaxies, as collections of stars, rearrange. The individual stars, as physical objects, continue their lives. The two scales of physics, the galactic and the stellar, are largely decoupled. This is what makes the merger non-threatening in any urgent sense. Individual stars, including our own, are largely unaffected by the merger. The merger is a large-scale gravitational rearrangement. It is impressive on cosmic timescales. It is not, for any particular star, a catastrophe. Let me hold what this means in terms of the typical experience of stars in merging galaxies. A star's life is governed by its mass and its internal physics. Hydrogen fusion in the core proceeds at a rate determined by gravity and quantum mechanics. Energy is generated, transported outward through the envelope, and radiated away from the photosphere. The star evolves over millions to billions of years, depending on its mass. None of this depends on what is happening in the rest of the galaxy. A star in a merging galaxy goes through exactly the same internal physics as a star in any other galaxy. Its mass determines its lifetime. Its initial composition determines its color and luminosity. Its rotation rate sets its magnetic behavior. The merger changes the star's orbit within the galaxy. The merger may bring the star closer to or farther from the galactic center. The merger may change the star's relationship to neighboring stars. But the merger does not affect the star's interior in any meaningful way. This is one of the elegant features of stellar physics. Each star is its own self-contained physics experiment. The experiment continues regardless of what happens around it, as long as no other star or compact object approaches close enough to disrupt it. For our Sun, this means that the upcoming merger of M31 with the Milky Way is largely irrelevant to its evolution. The Sun will continue to fuse hydrogen as long as its core supports the reaction. The Sun will then transition through its giant phases, regardless of what is happening in the larger galaxy. The Sun will end its life as a white dwarf, again regardless of the merger. The Sun's life cycle and the galaxy's merger are, in this sense, two parallel processes. They unfold on similar timescales, but they are largely independent. Hold this. The story of the merger is, in this sense, a story of scale. At the scale of the galaxy, the merger is a transformative event. At the scale of the individual star, the merger is a slow background change. At the scale of the planet, the merger is mostly irrelevant. Other effects, like the host star's own evolution, dominate. We are interested in the merger because we are interested in the cosmic scale of things. We want to understand the long arc of how galaxies evolve. The merger is part of that story. But we are not, in any practical sense, threatened by it. The timeline is far, the dynamics are slow. The individual stellar evolution proceeds independently. We are observers of a slow cosmic event. We are watching it unfold over billions of years. The unfold is what we are walking through tonight. Let me also walk through the question of what dark matter does during the merger. The dark matter is, by mass, the majority of the matter in both galaxies. The dark matter halos of M31 and the Milky Way are each much larger than the visible disks. The halos extend roughly 1 million light-years out from each galaxy's centre, possibly more. When the two galaxies approach, the dark matter halos are the first to interact. The halos overlap when the galaxies are still hundreds of thousands of light-years apart. The dark matter, however, does not collide in the same way the visible matter does. Dark matter particles, by current understanding, do not interact with each other except through gravity. They pass through each other freely. But the gravitational interaction between the two halos is significant. The halos exchange angular momentum. The orbital trajectories of dark matter particles are deflected. The halos, over the course of the merger, gradually merge into a single larger halo. This process is, in some sense, the dominant gravitational dynamics of the merger. The visible matter, the stars and gas, follows along. The visible matter is, in some sense, just markers of where the underlying dark matter is. The merger is, primarily, a merger of dark matter halos. The visible parts of the galaxies are secondary. The stars and gas track the gravitational potential set by the dark matter, but they are not themselves the main mass. By the end of the merger, the combined halo will contain all the dark matter from both original halos. The new halo will be larger and more massive than either parent. It will, over time, settle into a stable configuration determined by the merged gravity. The visible parts of the merger product will, similarly, be the combined stars and gas of both galaxies. They will be redistributed according to the new gravitational potential. They will, eventually, settle into the elliptical galaxy configuration. This is the underlying picture. Most of the action, in some sense, is in the dark matter. The visible parts are the consequence. Now let me pull back, fellow night watcher. I want to spend some time on the broader picture of galaxy mergers in cosmic history, because they are not rare events. They are part of how galaxies grow. In the standard model of galaxy formation, galaxies grow by two processes. The first is in situ growth, in which gas falls into a galaxy and forms new stars. The second is merger growth, in which two galaxies come together and combine. Both processes are important. Both have shaped the population of galaxies we see today. For most large spiral galaxies, including the Milky Way and M31, the growth history involves multiple major and minor mergers over cosmic time. Each merger contributed stars, gas, and dark matter to the growing galaxy. Each merger left signatures in the present-day structure in the form of stellar streams, gravitational halos, and dynamical features. Looking at the Milky Way today, we can identify the signatures of past mergers. The Sagittarius dwarf galaxy, currently being torn apart by our gravitational pull, is a recent example. Over the past billion years or so, the Milky Way has been gradually absorbing the Sagittarius dwarf, with its stars being pulled into a vast stellar stream that wraps around the Milky Way. The stream is visible in current surveys. Other, larger mergers have happened in our galaxy's past. About 10 billion years ago, the Milky Way merged with a galaxy now called Gaia Enceladus, which contributed a significant fraction of the stars in our halo. The Gaia satellite identified this merger by detecting the unusual orbits of certain halo stars that trace back to a single ancient event. The current Milky Way is, in some sense, the product of many such mergers. It is not a pristine original galaxy. It is a composite built up by gravitational accumulation over 13 billion years. M31 has its own merger history, similar in broad outline. M31 has been growing by mergers throughout its existence. The merger of M31 with the Milky Way, 4.5 billion years from now, is, in this picture, the next chapter in a long sequence. It is not a unique event. It is not unusual. It is the natural fate of two large galaxies that find themselves close together in a gravitationally bound system. What happens after the merger is, by current models, a settling into a quieter elliptical phase. The merger product, having no significant infall in gas, will not form many new stars. The existing stars will gradually age and dim. The galaxy will become redder and dimmer over time, settling into the typical fate of large ellipticals. This is the long-term cosmic fate of our galaxy. We are heading toward a merger. The merger product will be an elliptical. The elliptical will, over many tens of billions of years, gradually fade. It is, in some sense, the cosmic equivalent of a long, quiet retirement. Stay with me here. Let me also walk briefly through what happens to the central supermassive black holes during the merger. Each of the two galaxies hosts a central supermassive black hole. The Milky Way has Sagittarius A star at 4.3 million solar masses. M31 has its central black hole at 150 million solar masses. The two holes will, during the merger, eventually come together. The process by which two supermassive black holes merge is, in some sense, an extreme version of what happens to the galaxies as wholes. The two holes sink to the center of the merger product over time, drawn by gravitational dynamics. They first form a wide binary system, orbiting each other at a distance of perhaps a few parsecs. The binary, over time, hardens, with the two holes spiraling closer. The final stages of the merger involve emission of gravitational waves. The two holes spiral together over the last few thousand orbits, emitting waves at frequencies that, if produced in our era, would be detectable by current gravitational wave observatories like LIGO and Virgo. The merger itself produces a brief but intense burst of gravitational waves. For our particular merger, the burst will occur far in the future. We will not detect it. But other observers, elsewhere in the universe, might detect similar bursts from galaxy mergers in their own cosmic neighborhoods. The detections, when they happen, will tell us much about how supermassive black holes merge. The result of the merger is a single supermassive black hole at the center of the merger product. The new hole inherits the mass of both parents, plus contributions from any gas that has been accreted during the merger. The new hole will, by best current estimates, be perhaps 200 million solar masses or so. This is one of the cosmic consequences of the merger, a new, larger supermassive black hole at the center of a single new galaxy. Now let me sit with what this means philosophically. For most of human history, we did not know that galaxies existed. The Milky Way was, in our cosmology, the universe. Other faint patches of light in the night sky were, in earlier conceptions, just clouds of gas and dust within our own galaxy. The recognition that other galaxies exist, accomplished in the 1920s, transformed our picture of the universe. We are not the universe. We are one galaxy among many. Each galaxy is a vast system of stars in its own right. The further recognition that galaxies interact, that they collide, that they merge, has been a development of the last several decades. The simulations have been done. The observational evidence has been collected. The picture has refined. We now understand that galaxies are not static eternal objects. They are dynamic, they evolve, they grow, they merge. They are, in some sense, part of a vast gravitational dance that has been ongoing throughout cosmic history. M31 is approaching us as part of this dance. The Milky Way and M31 are bound. The dance has begun in some sense billions of years ago, when our two galaxies first formed in the early universe. The dance will continue, with various passages and interactions for billions of years more. The dance ends in the standard picture with a merger. This is the cosmic position. We are partners in a long, slow gravitational engagement. Let me hold one more time the relationship between us and our cosmic neighbour. M31 is, in some sense, our cousin galaxy. We share a common cosmic environment. We have evolved in parallel over billions of years. We have grown by similar processes. We have similar structures. The merger that will eventually unite us is, in this sense, a reunion. Two cousins who have been falling toward each other for billions of years will finally meet. The meeting will transform both. The transformation will produce something new. This is the cosmic narrative. Two galaxies, long parallel evolution, eventual merger, single product. The narrative is, in some sense, peaceful. The galaxies are not in conflict. They are simply, by the dynamics of gravity, drawn together. The drawing has been slow, the encounter will be slow, the aftermath will be slow. We sit in our small slice of the long story, watching the approach. The watching's what we can do. The watching's enough. The engagement has its choreography. We are following the steps. Hold this. The choreography is, in some sense, the natural unfolding of gravitational dynamics. There is no choice, there is no decision. The gravitational laws set the trajectory. The trajectory leads to a merger. We are, in this sense, passengers. The galaxy carries us along. The motion is not under our control. The future is largely set by cosmic dynamics, not by any decision we might make. This is, in some ways, humbling. It is also, in some ways, peaceful. The cosmic timescale of the merger is so long that it does not, in any urgent sense, affect our daily lives. We watch the slow approach, we measure, we model, we learn. The merger arrives on its own schedule, far in the future. We do what observers do. We notice, we record, we try to understand. The understanding is ours, the merger is the universe's. Now let me come back to the distance. The distance, as I mentioned, is 2.5 million light years. The light we see now left M31 2.5 million years ago. We see the galaxy in its past. This is true of all astronomical observation. Every photograph of every distant object is, in some sense, a photograph of the past. The further the object, the further the past. Galaxies at the edge of the observable universe show us light from when the universe was a few 100 million years old. M31, by comparison, shows us light from a relatively recent epoch. What we cannot see when we look at M31 is what it looks like now. The current state of M31 is unknown to us. The light from that current state is still in transit. It will arrive eventually 2.5 million years from now. But by then our descendants, if any, will be watching something else. The now of M31 is, in some real sense, inaccessible to us. We have the M31 of 2.5 million years ago. That is what our telescopes show. That is the data we have. For most purposes, the difference does not matter. M31 has not changed appreciably in 2.5 million years. The galaxy is roughly the same. The stars in it have continued their lives mostly. The structure has evolved slowly, if at all. The 2.5 million year delay is, in cosmic terms, a small one. But it is worth holding the fact that the delay exists. We are not, in any strict sense, seeing M31 as it is. We are seeing M31 as it was. The difference is small, but it is real. The motion of M31 toward us has been continuing during the 2.5 million years that the light has been travelling. M31 today is closer to us than the M31 we currently see. The closing of the distance has been ongoing. This is one of the textures of looking at distant objects in motion. Their position when the light left them is not their position now. The current position is, in some sense, ahead of the position we see. For the gradual merger trajectory, the delay does not matter much. The trajectory unfolds over billions of years. A 2.5 million year delay is a small fraction of the total time. The picture is essentially the same. But it is, when we sit with it, an interesting feature. The galaxy we see is not where it is. The galaxy is where we see it, plus the motion that has occurred during the light travel time. Now let me bring this closer. I want to walk through what the merger will look like from the perspective of an observer on Earth, if any such observer were still here to watch. Let me also walk briefly through what the merger means for the gas content of the future galaxy. The gas in galaxies is, in some sense, the raw material for new stars. Galaxies that retain gas continue to form new stars over cosmic time. Galaxies that lose gas by various mechanisms stop forming stars. Both M31 and the Milky Way currently have significant gas reservoirs. The Milky Way contains roughly 10 billion solar masses of cold gas, distributed in clouds along the spiral arms. M31 contains a similar amount, perhaps somewhat more. During the merger, much of this gas will be consumed in the starburst phases. The compressed gas in the colliding regions will form new stars rapidly. The most massive of these stars will explode as supernovae, blowing some of the gas out of the galaxy entirely. By the time the merger completes, the gas reservoirs of the merger product will be largely depleted. Some gas will remain, but at reduced levels. New star formation will slow significantly. This is one of the reasons that the merger product becomes an elliptical. Elliptical galaxies are gas poor. They do not form many new stars. The merger has, in some sense, exhausted the gas that would otherwise have sustained ongoing star formation. The transition from gas-rich spiral to gas-poor elliptical is, in cosmic terms, one of the major transformations that galaxies undergo. The merger is the typical trigger. After the merger, the gas-poor elliptical galaxy will, over hundreds of millions of years, settle into the configuration we see in current elliptical galaxies elsewhere in the universe. The galaxy will be reddish, dim relative to its size, dominated by old stars, with little or no ongoing star formation. This is what our future will look like 6 or 7 billion years from now. A quiet, old, gas-poor galaxy, where the once active Milky Way used to be. The first noticeable change will be in the apparent size of M31 on the sky. Currently, M31 occupies an angular extent of roughly 3 degrees on the sky. That is 6 times the diameter of the full moon. The angular size is set by the physical size of M31 and the distance to us. As M31 approaches, the distance decreases. The angular size grows. Over the next 4.5 billion years, the angular size will increase from 3 degrees to perhaps 10 or 20 degrees, depending on the exact trajectory. By the time of the first close passage, M31 will fill a substantial portion of the night sky. The visible structure of M31 will become more detailed as the angular size grows. The spiral arms, currently visible only through telescopes, will become resolvable to less powerful instruments. The central bulge will appear bright. Individual bright star clusters within M31 will become distinguishable to careful observers. Let me hold the current view of M31 for a moment. From a dark site on Earth tonight, in the autumn, you can see M31 with the naked eye if you know where to look. It is in the constellation Andromeda, slightly above the V shape of the constellation. It appears as a small faint smear of light, slightly elongated, with a brighter centre. The faint smear is 1 trillion stars. The stars are gravitationally bound. They have been orbiting the centre of M31 for billions of years. Some of them are similar to our Sun. Some are giants, some are dwarfs. Most are middle-aged. A small telescope, even a modest amateur instrument, can resolve more detail. The central bulge of M31 is bright in a telescope. The spiral arms faint can be seen with patience and good equipment. The companion galaxies M32 and M110 are visible as smaller, fainter blobs near the main galaxy. A larger telescope, or careful long exposure imaging, reveals much more. The full extent of the disk, individual bright star clusters, the dust lanes that wind through the arms, the texture of the galaxy's structure. What you see in any of these observations is M31 as it was 2.5 million years ago. The light has been travelling for that time. The observation is, in some sense, archaeological. You are looking at a recording of how the galaxy looked at that particular moment in its history. M31 today is, presumably, broadly similar to what we see. Galaxies do not change much in 2.5 million years. The orbits of the stars within them are stable on timescales of tens of millions of years. The structural features, the disk, the arms, the bulge, are essentially fixed on the timescales we are discussing. But M31 today is closer to us than the M31 we see. The approach has been continuing during the light travel time. M31 today is, roughly, 230,000 light-years closer to us than what our telescopes show. The closing has covered that much distance during the time the light has been travelling to us. This is one of the textures of looking at moving objects. The position when the light left and the position now are different. The difference is small here, but it is real. For an observer on a planet orbiting a star somewhere in our galaxy, sometime in the next 4 billion years, the night sky will gradually transform. The familiar constellations will remain. The Milky Way will continue to arch across the sky as a band of stars. But M31, that small, faint smear we see now, will grow into a vast, pale shape, a sister galaxy slowly closing in. By the first close passage, M31 will look truly enormous. The two galaxies will be visibly interacting. Tidal streams of stars will arc across the sky. Bursts of star formation, triggered in compressed gas clouds, will produce bright clusters and pinkish ionized regions. The view, from anywhere with a clear night sky, will be spectacular. The galaxies will be intertwined. The sky will look, in some sense, full of cosmic activity. Let me hold what the first close passage will look like in slightly more detail. The two galaxies will approach each other at substantial speed. The centers will pass within roughly 100,000 light-years, which is approximately the diameter of the Milky Way. At that distance, the gravitational pull of each galaxy on the outer regions of the other will be strong enough to severely distort both structures. The spiral arms of each galaxy will be torn outward by tidal forces. Long tidal streams of stars will extend across hundreds of thousands of light-years on either side of the merging system. The streams will form vast arcs in the sky, visible from any location with a telescope. Within the galaxies themselves, dense gas clouds will compress against each other. The compression will trigger massive starbursts. New stars will form rapidly, in bright young blue clusters. The most massive of these stars will burn through their fuel quickly, ending as supernovae within tens of millions of years. The sky, during this phase, will be punctuated by these supernovae. From any planet within either galaxy that retains a clear atmosphere, the supernovae will appear as bright transient stars, occasionally outshining all the others in the sky. The supernova will be more common than now, due to the elevated star formation rate. The total visible energy output of the merging system during the first close passage will be elevated. The merged galaxy will appear as a particularly bright luminous infrared galaxy, the type of object we observe today in various places in the universe as templates for what mergers in progress look like. After the first close passage, the galaxies will separate. The view will gradually shift back to something simpler, as the two systems briefly pull apart before falling back together. The second close passage, about 1 billion years after the first, will produce a similar but more chaotic view. By then, the gas distribution within the merging system will have been disrupted further. Star formation will be even more intense. The merger will be visibly progressing. The final coalescence, about 6 to 7 billion years from now, will produce a single large elliptical galaxy. The disks will have been destroyed. The stars will be in random orbits. The galaxy will, over the subsequent few hundred million years, settle into a relatively quiet state. The sky, from the perspective of an observer at this point in cosmic history, will be different from what we see now. There will be no Milky Way arching across the sky. There will be no M31. There will be, instead, a large elliptical galaxy filling a major portion of the sky in many directions, depending on the observer's location within the merger product. This is the projected long-term view. This is what the merger looks like. But, again, all of this is far in the future. No observer on Earth will see any of it. The Sun will have moved through its red giant phase long before the merger completes. Earth will not be habitable for any observers of our biological kind by the time of the first close passage. The merger is a cosmic event, observed by us only in projection, through models and simulations. The actual viewing of the merger, if it occurs, will be by observers in some other place, perhaps in some other star system, perhaps not biological at all. We do not, in any meaningful sense, witness the merger. We anticipate it. We model it. We work out what it will look like, but we do not see it. Let me also walk briefly through what we have learned from observations of other galaxy mergers in progress elsewhere in the universe. The universe contains many galaxy mergers at various stages. By observing these, we have built up our understanding of what mergers look like and how they unfold. The antennae galaxies in the constellation Corvus are perhaps the most studied galaxy merger in the local universe. The two galaxies, NGC 4038 and NGC 4039, are in the midst of an active merger. They have already undergone their first close passage and are now in the second approach. Tidal streams of stars extend across vast regions of the sky. Bursts of star formation are visible across the merging system. The antennae have been imaged in detail by the Hubble Space Telescope. The images show the merger in progress, with clear structural distortions, tidal arms, and starburst regions. The observations have informed simulations and theoretical models of how mergers unfold. Other well-known mergers include the mice galaxies, NGC 4676, and various pairs in the Hercules cluster. Each provides additional data on the merger process at various stages. These observations, combined with simulations, give us a clear picture of what the M31 and Milky Way merger will look like at various stages. The first close passage will produce features similar to those visible in the antennae today. The second close passage will continue the pattern. The final coalescence will produce the elliptical galaxy structure. The picture is, in some sense, well developed. We have detailed observations of mergers in progress. We have simulations that reproduce the observed features. We have theoretical understanding of the underlying dynamics. The merger of M31 and the Milky Way, while far in the future, can be modelled in detail. This is what modern observational and theoretical cosmology can do. We see the future, in some sense, by observing analogous events happening now and by extrapolating with our models. The future is not unknown. It is, to a significant degree, predictable. What we cannot predict in detail is what will happen to any individual star or planet. The bulk dynamics are clear. The specific microscale outcomes are uncertain, but the broad picture is firm. Now let me hold the implications for our place. We are bound to M31. The two galaxies are gravitationally locked. The dance is set. The trajectory leads to a merger. This is, in some ways, a deep feature of our cosmic position. We are not alone in the local group. We are not isolated. We have a partner, and the partner is approaching. Most galaxies in the universe are not as close to another major galaxy as we are. Many galaxies sit in relative isolation, separated by tens of millions of light years from their nearest neighbours. The local group is, in this sense, a relatively crowded environment. The crowding is not a coincidence. Galaxies form preferentially in groups, drawn together by the same large-scale gravitational structures. The local group exists because the cosmic web has, in our particular region, produced a relatively dense pocket of galaxies. We are part of that pocket. M31 is part of that pocket. The smaller galaxies of the local group are also part of it. We are bound, all of us, by the gravity of the dark matter that surrounds us. The merger of M31 with the Milky Way is, in this picture, the inevitable consequence of being part of a small bound system. The smaller members of the local group will, over time, also fall in. The merger product will eventually absorb most of them. The local group will, in many billions of years, become a single large elliptical galaxy. The constituent members will have merged. The resulting object will sit alone, in its corner of the universe, slowly aging and fading. This is the long-term fate of the local group. This is what we are part of. Stay with me here. Let me also walk through some details of what M31 contains, because the galaxy is, in some sense, the closest cosmic neighbour we have at this scale. M31 contains, as I mentioned, approximately 1 trillion stars. The stars are organised in the classic spiral structure, with a central bulge, an extended disk, and several pronounced spiral arms winding outward from the centre. The arms contain younger blue stars, regions of active star formation, and considerable dust. The central bulge of M31 is quite prominent. It contains older, redder stars. The bulge is roughly 5,000 light-years across. The central supermassive black hole sits within this bulge. Around the disk of M31 lies an extended halo of older stars. The halo extends roughly 220,000 light-years out from the centre. Within the halo are several smaller satellite galaxies, including M32 and M110, both of which are dwarf elliptical companions to M31. M31 also has other smaller satellites, some of which are being tidally disrupted by M31's gravity. The dynamics of M31's satellite system are themselves interesting. The satellites are, in some sense, the test particles by which M31's gravitational mass can be measured. The motion of the satellites tells us how much mass M31 contains, including dark matter. By combining the satellite dynamics with various other measurements, we've built up a detailed picture of M31's total mass distribution. The dark matter halo of M31 extends well beyond the visible galaxy. The halo is roughly 2 to 3 times the radius of the visible disk. It contains the majority of M31's mass. By current estimates, the dark matter halo of M31 may extend close enough to overlap with the dark matter halo of the Milky Way already. If this is correct, the two halos are already in some early stage of interaction, even though the visible disks are still far apart. This is one of the more startling aspects of the merger picture. The dark matter halos may already be touching, the visible galaxies are far apart. But the gravitational dynamics dominated by dark matter is already an early merger. Let me also walk briefly through how we have come to understand all of this. The understanding has been built up over the past century. The first step was Hubble's recognition that M31 is a separate galaxy. That was 1923. The second step was the measurement of M31's radial velocity, showing that it is approaching us. That was earlier in 1912. The third step was the modern measurement of M31's tangential velocity, showing that the approach is roughly head-on. That was 2012. Between these key moments, many smaller refinements have accumulated. The distance to M31 has been measured many times with progressively better precision. The mass of M31 has been determined by various techniques. The structure of M31, both visible and dark, has been mapped in detail. The simulations of the merger have been run by many groups with increasing sophistication. The cumulative picture, after roughly a century of work, is the one I have been walking through. M31 is approaching. The merger is inevitable. The timeline is 4.5 to 7 billion years. The result is a single large elliptical galaxy. The picture is robust. It rests on many independent lines of evidence. It is consistent with the broader understanding of galaxy evolution. It may be refined further. The exact timing of the first close passage may shift by a few 100 million years. The detailed structure of the merger may be different in different simulations. The future location of the Sun within the merger product is uncertain by light years, but the broad outline is settled. M31 is coming. The merger will happen. The merger product will be an elliptical. This is what we know. Let me also walk briefly through the simulations that produce the merger prediction. The predictions about the merger are not based on direct extrapolation of M31's current motion. They are based on detailed numerical simulations that include the gravitational dynamics of all the major components. A typical merger simulation involves modelling M31 and the Milky Way as collections of particles. Each galaxy is represented by perhaps a few 100 million particles, distributed in disk, bulge, and halo configurations. Each particle is given a position and velocity, and the gravitational interactions between all pairs of particles are computed. Computing the interactions between hundreds of millions of particles is computationally expensive. Simulations of this type require supercomputers and run for weeks or months at a time. Team, various sophisticated algorithms like tree codes and particle mesh methods are used to reduce the computational cost. The simulations are run with a range of initial conditions, reflecting the uncertainties in our current measurements. Different runs use different values for the relative velocities, different values for the mass distributions, different values for the dark matter halo extents. The cumulative ensemble of runs gives a probability distribution for the future trajectory. The robust prediction, across all reasonable initial conditions, is that the merger will happen. The exact timing varies by perhaps 1 billion years across different runs. The exact final configuration varies in detail. But the general outcome is consistent. M31 and the Milky Way merge. The simulations also predict in detail what the merger will look like at various stages. The visualization of these simulations has been a popular subject for astronomy outreach. Anyone interested can find videos showing the simulated merger unfold over billions of years, compressed into a few minutes of viewing. The simulations are, in some sense, our best approximation of what will happen. They are not perfect. They make assumptions. They simplify some aspects of the physics, but they are detailed enough to give us a clear qualitative picture and reasonable quantitative estimates. This is the modern state of merger prediction. We have detailed simulations. The simulations give consistent results. The picture is clear. Now let me bring this closer. I want to hold the question of what it means that the merger is so far in the future. 4.5 billion years is a long time. It is roughly the age of the Earth. It is roughly the time elapsed since the formation of our solar system. It is many times the duration of the history of life on Earth. Within 4.5 billion years, an enormous amount can happen. On Earth, biological evolution will continue. Species will rise and fall. Climate will change. Continents will drift. The sun will gradually grow brighter, eventually rendering the surface of Earth uninhabitable, perhaps within 1 billion years. After Earth becomes uninhabitable, in roughly 1 billion years, the planet will continue to exist. It will be a rocky body in orbit, baked by an increasingly brighter sun, perhaps with a thin atmosphere of vaporized rock. By 4 billion years from now, when the sun begins its red giant transition, the Earth will likely be engulfed. Through all of this, M31 will be approaching. The light we see from M31 has been on its way for 2.5 million years. The light we will see from M31 in 1 billion years will have been on its way for that same duration. But the galaxy will have closed in by hundreds of thousands of light years by then. The approach is slow. The approach is steady. The approach continues, regardless of what happens on any particular planet. This is the cosmic patience. The merger does not hurry. The merger has its schedule. The schedule unfolds over billions of years, independent of biological history. Let me also hold what the closing of the distance looks like on shorter timescales. From now to the first close passage is about 4.5 billion years. The current distance is 2.5 million light years. The closing rate at the radial component of 110 kilometers per second is approximately 110 kilometers each second. Per year, that is roughly 3.5 billion kilometers. Per million years, 3 quadrillion kilometers. Per billion years, 3 quintillion kilometers. Over 4.5 billion years, the cumulative radial distance covered is roughly 15 quintillion kilometers, or about 1.5 million light years. The closing covers roughly half of the current distance, over 4.5 billion years. The remaining distance, plus the effects of the tangential motion, brings the galaxies to the first close passage at the end of that time. The picture is, in some sense, of a slow, inexorable drift. The motion is constant on the relevant timescales. The distance reduces, the encounter approaches. This is what the dynamics look like: slow, steady, inevitable. We watch from our planet. The closing continues. We measure the closing more precisely with each passing year of observation. The picture sharpens. We sit in our small slice of time, watching the approach. We measure the velocity. We model the trajectory. We anticipate the outcome. But the merger itself, when it arrives, will be observed only by whatever observers exist in that distant epoch. Not us, not our biological descendants, in any meaningful sense. It is, in some sense, an event we know is coming, but will not see. Let me hold that for a moment. We know it is coming. We have measured it. We have modelled it. We have detailed expectations about what will happen. We will not see it. The merger is too far in the future for any plausible biological observer of our kind. The merger will happen long after the sun has retired, long after Earth has been engulfed, long after any conceivable continuation of our biosphere. But we know about it. We have in some sense glimpsed the long arc. This is one of the strange textures of cosmic understanding. We can see the future in some sense by understanding the dynamics that produce it. We can see past the limits of our own existence by careful application of the physics we have learned. The future of the local group is, in this picture, available to us. We know what will happen, we just won't be there to see it. Stay with me here. Let me also walk briefly through what the merger means in the broader cosmic narrative. Galaxy mergers are one of the major processes that have shaped the current population of galaxies in the universe. By understanding mergers, we understand how galaxies got to be the way they are. Most large elliptical galaxies in the current universe are believed to be the products of past mergers. Many large spirals have had minor mergers in their past. Even the Milky Way, as I mentioned earlier, has merged with several smaller galaxies in its long history. The cosmic merger rate has been higher in the past than it is now. In the early universe, when galaxies were closer together on average, mergers happened more frequently. Many of the current population of galaxies are the products of merger sequences that began billions of years ago. The merger of M31 with the Milky Way will, in some sense, contribute to this broader cosmic process. It is one event among many. It is not particularly unusual. It is the natural outcome of the gravitational dynamics that have been shaping galaxies throughout cosmic history. What is somewhat unusual about our merger is that we get to anticipate it. We can model it in detail. We can predict the outcome. Most galaxy mergers happen too far away for us to study in real time. Ours is one of the closest and one of the best studied. The detailed predictions of our merger are, in some sense, the cumulative culmination of 100 years of cosmological research. The first measurement of M31's distance in 1923. The first measurement of its radial velocity somewhat earlier. The first measurement of its tangential velocity in 2012. The simulations ongoing for several decades. We are at the point where we can describe in detail what will happen to our galaxy 4.5 billion years from now. This is, in some sense, a remarkable position to be in. We can see through our models far into the future of our own cosmic environment. This is, in some ways, what science gives us. The ability to extend our awareness beyond our own immediate experience. The ability to see, through the mind, what we cannot see through the eye. We see the merger of M31 with the Milky Way, in this sense. Not directly, not in light, but through model and simulation, through the careful application of the gravitational equations we have inherited from past generations. The merger is real. The merger is inevitable. The merger is coming. We are watching it approach, slowly, over the course of 2.5 million light years and 4.5 billion years. This is what we are doing tonight. Let me also walk briefly through the gas dynamics during the merger. The gas in each galaxy, unlike the stars, is collisional. The gas in M31's interstellar medium will, when the two galaxies pass through each other, collide with the gas in the Milky Way's interstellar medium. The collisions will compress the gas, heat it, and trigger bursts of star formation. The first close passage will produce a major starburst. The compressed gas in the colliding regions will form new stars at rates far higher than current rates in either galaxy. The new stars will be bright, blue, and massive. They will, in some cases, end their lives as supernovae within tens of millions of years. The merger product will, during the active merger phase, look something like a luminous infrared galaxy. Vast amounts of dust will be produced by the dying massive stars. The dust will absorb optical light and re-radiate it in the infrared. The galaxy will be bright in the infrared, perhaps detectable by external observers across hundreds of millions of light years. After the merger completes, the starburst will subside. The gas reservoirs will be depleted. New star formation will slow. The galaxy will, over hundreds of millions of years, transition from active luminous merger to quiet aging elliptical. This is the typical sequence for galaxy mergers: active phase, starburst, quenching, elliptical end state. For our particular merger, all of this is, again, far in the future. We will not see any of these phases directly. We only know about them through theoretical models and observations of other galaxy mergers in the universe. Other galaxies currently undergoing mergers at various stages can be observed and studied. They provide templates for what our future will look like. The templates are well developed. The expectations are firm. Now let me also walk through what the cosmic web around us looks like, to give a sense of where the local group sits. The local group is part of a larger structure called the Virgo supercluster. The Virgo supercluster spans about 100 million light years and contains the local group plus many other groups and clusters. The dominant member of the Virgo supercluster is the Virgo cluster itself, about 60 million light years away from us, containing perhaps 1,000 galaxies. The Virgo supercluster is, in turn, part of an even larger structure called the Laniakea supercluster, identified in 2014, and Laniakea spans about 500 million light years and contains the Virgo supercluster plus several neighbouring superclusters. The Laniakea supercluster is, by current understanding, a single coherent gravitational structure, in the sense that its members are flowing together toward a common gravitational centre. Within Laniakea, the Milky Way and M31 site gravitationally bound in the local group. The local group, in turn, is being drawn toward the Virgo cluster by gravitational pull. The flow is slow, but it is real. So the picture, at the larger scales, is one of nested gravitational attractions. The local group sits inside the Virgo supercluster. The Virgo supercluster sits inside the Laniakea supercluster. The Laniakea supercluster sits inside the broader cosmic web. Within all of this, the merger of M31 and the Milky Way is one of many gravitational events that will unfold over cosmic time. The merger is, in some sense, a local affair. It involves only our two galaxies. The broader cosmic structure continues regardless. But for us sitting in the local group, the merger is the most consequential gravitational event in our near future. It is the thing that will eventually transform our galactic environment. We are at the early stage of that transformation. The two galaxies are still separated by 2.5 million light-years. The collision is still 4.5 billion years away. The full merger is still 6 to 7 billion years from completion. We have time, we have so much time. Now let me hold the philosophy of this for a moment. The merger of two galaxies is, in some sense, a process of integration. Two systems with their own histories, their own structures, their own internal dynamics, come together over the course of billions of years. The integration involves a substantial rearrangement of all the constituent parts. By the end, neither original system can be identified within the merged product. This is, in some ways, the cosmic equivalent of two cultures merging over generations. Each contributes, each is transformed. The result is a new system that, in some sense, contains both but is identical to neither. For our galaxy, the merger with M31 will be the largest gravitational event in our history. The Milky Way has had mergers before with smaller galaxies. The merger with M31 is the major one. After it, the Milky Way will no longer exist as a distinct entity. There will be only the merger product. This is, in some sense, the end of the Milky Way as we know it. The end is not catastrophic. The end is not sudden. The end is a slow transformation into something different. The new thing will contain everything that is currently in the Milky Way. The stars, the remnants, the dark matter halo, the whole structure, plus everything that is currently in M31. All of it will be combined into a single object. The object will be different from either parent, but it will contain both. This is the long arc. Let me also walk through the question of what the merger product will look like in the distant future, after all the dynamics have settled. The final product after the merger completes and the dynamics relax will be a large elliptical galaxy. Elliptical galaxies are common in the universe. They are found in galaxy clusters, where mergers have happened often. They are typically older than spirals, with less ongoing star formation. The new galaxy will contain approximately 1.25 trillion stars, the combined stellar populations of M31 and the Milky Way. The stars will be in random orbits, not organized in a rotating disk. The galaxy will have a roughly spheroidal shape, perhaps slightly flattened due to residual rotation from the parent galaxies. The age distribution of stars in the merger product will reflect the merger history. Older stars from the original galaxies will be common. A burst of younger stars formed during the merger from compressed gas will provide a distinctive population. The younger stars will be those formed during the active merger phase, perhaps over a period of 1 or 200 million years. The chemistry of the merger product will be a mix of the chemistries of the parent galaxies. Both are roughly similar in chemical composition, so the mix will not be dramatic. The merger product will be somewhat more metal-rich than either parent, due to the new generation of stars formed from chemically enriched gas. The central supermassive black hole will be at the center of the new galaxy. It will continue to accrete material slowly. It will, occasionally, produce minor bursts of activity. But the bright quasar phases will be in the past. The black hole will be quiet. Over many tens of billions of years, the merger product will gradually evolve. The most massive stars will burn out and disappear. The galaxy will become redder, dimmer, less active. Star formation will slow to near zero. The galaxy will, in some sense, retire. This is the eventual fate. The galaxy ages. The galaxy fades. The stars wink out, one by one, over hundreds of billions of years. The black hole at the center, by some very distant epoch, evaporates by Hawking radiation, but that timescale is so long it transcends ordinary cosmological discussion. This is the long arc of our galactic future, from two large active spirals to a single merging system, to a single quiet elliptical, to a slowly fading old galaxy. The full sequence takes tens to hundreds of billions of years. We are at the very beginning of this sequence. We see the two spirals, separated by 2.5 million light-years, approaching each other. We model what comes next. We anticipate the long, quiet evolution. The work of modeling all of this is, in some sense, the work of cosmology. We piece together what will happen. We work out the consequences. We add to the human understanding of the deep future of our cosmic environment. The understanding is partial. The understanding is provisional. But it is real. It is the best account we have so far. Let me sit with the cosmic patience of all of this. The universe does not hurry. The galaxies do not rush their dances. The merger unfolds at the pace that gravity sets. We, watching from a small planet in one of the galaxies, see only the very beginning. We see the approach. We anticipate the rest. We extend our awareness through models. What the actual observers, billions of years from now, will see, we can only imagine. What we do is what we can do. We measure. We model. We learn. We add to the cumulative human understanding of the cosmic context in which we sit. This is the work. This is what we do tonight. Let me hold the timing more carefully. 4.5 billion years is, in cosmic terms, a substantial duration. The age of our solar system is approximately 4.5 billion years. The merger is, in some sense, approximately one solar system age from now. This is the same scale as the time elapsed since the formation of our planet. The Earth, in the 4.5 billion years since its formation, has undergone enormous change. Continents have drifted. Climates have shifted. Life has evolved from single cells to multicellular forms to intelligent beings. The biosphere has been transformed. If we project a similar amount of change into the future, in the next 4.5 billion years, the Earth will be utterly different by the time of the merger. Whatever life remains, if any, will have evolved into forms unrecognizable to us. The continents will have drifted into new configurations. The climate will have changed in ways we cannot fully predict. The sun, during this time, will have brightened steadily. The increasing solar luminosity will, within roughly 1 billion years, render the Earth's surface too hot for liquid water. The biosphere as we know it will end at that point. After the biosphere ends, the Earth will continue as a sterile baking rock for several billion more years. Eventually, in roughly 7.5 billion years, the Sun will expand into a red giant and engulf the inner planets. Earth will likely not survive this expansion. The merger, 4.5 billion years from now, will occur within this broader stellar evolution. The first close passage will happen while Earth is still in its sterile baking phase, before the red giant expansion. The full merger will complete during or after the red giant phase. This is the overlap. This is the merger and the Sun's evolution play out on similar timescales. Both will reshape our local cosmic environment in fundamental ways. For us, in our small moment of time, the merger is a future event. We can model it, we can anticipate it, we will not see it, but it is coming. Let me hold one more time the gentle quality of the approach. M31 is approaching us, yes. The radial velocity is 110 kilometers per second. That sounds fast on human scales. On cosmic scales, it is slow. Light travels at 300,000 kilometers per second. M31 is approaching at 1 part in 2,700 of the speed of light. The approach is not dramatic. It is patient. The two galaxies have been falling toward each other under mutual gravity for billions of years already. They will continue to fall for billions more. The trajectory is set. The outcome is set. The pace is set. Nothing changes urgently. The motion is slow on every relevant timescale. The drama, if any, is in the cosmic span, not in any short interval. This is the gentle quality. The approach is real, but it is not threatening in any urgent sense. We have, in the most literal sense, all the time in the world, plus several more worlds, in fact. The cosmic event approaches. The cosmic event is patient. The cosmic event will arrive when it arrives, on its own schedule. We are watchers, not participants. Watchers in this position can be calm. The event is not ours to control. The event is the universe's. We notice it. We measure it. We anticipate it. We let it be what it is. Now let me come slowly to a quiet close. The galaxy approaching us is 2.5 million light years away. It is the largest galaxy in our local group. It has more stars than we do. It has more mass than we do. It is heading toward us at 110 kilometers per second on the radial component plus a tangential component. The merger is inevitable. The merger will happen in approximately 4.5 billion years for the first close passage. The full coalescence will complete in 6 to 7 billion years. By then, the Sun will already be a red giant. Earth will likely be uninhabitable or destroyed. The biosphere will be long gone. Let me hold what it means for our species. Humans, as a biological lineage, have existed for roughly 200,000 years in our current form. Our hominin ancestors go back perhaps 7 million years. Mammals, as a class, go back roughly 200 million years. In the 4.5 billion years until the first close passage of M31, the entire history of life on Earth could repeat several times. If we measure the duration in terms of major biological revolutions, the origin of multicellular life, the Cambrian explosion, the evolution of vertebrates, the rise of mammals, the emergence of human intelligence, we have time for many such revolutions before the merger arrives. Whether our particular lineage will continue for that long is uncertain. Many things could happen. Various extinction risks loom over biological civilizations. We cannot predict with any confidence that humans will exist in any recognizable form 4.5 billion years from now. But the cosmic timescale is what it is. The merger will happen on that timescale. The biological history that might unfold in the same span is enormous. Whatever observers might exist in that distant epoch will inherit the universe that gravity has prepared for them. For now, we are the observers. We sit in our small moment, watching the slow approach. We do what we can. We measure. We model. We anticipate. The work is ours. The merger is the universe's. The merger will produce a single large elliptical galaxy. The merger product will inherit everything from both parents. It will, over many tens of billions of years, gradually settle into a quiet, old galactic state. This is the cosmic position of our galaxy. We are partners in a long, slow gravitational engagement. If you have come here to rest, let this carry you. The galaxy approaching us is on a long, quiet trajectory. Nothing happens for billions of years. We sit in the meantime in the early evening of a vast cosmological story. The story is long. The pace is slow. The events are gravitational. The outcome is a merger. We are observers. We watch from our small planet. We measure. We model. We learn. The cosmic dance continues. The pace does not hurry. The choreography is set. We sit in the meantime, watching M31 approach. Let me hold once more the simple fact at the heart of all of this. There is in our autumn sky a galaxy. The galaxy contains 1 trillion stars. The galaxy is 2.5 million light years away. The galaxy is approaching us at 110 kilometers per second. These are simple statements. They are based on extensive measurement. They are well supported by independent lines of evidence. They are, by any reasonable standard, established. From these simple statements, by application of the known laws of gravity, we deduce the future. The future involves the merger. The merger leads to a single elliptical galaxy. The elliptical galaxy ages and fades over very long timescales. This is the chain of inference. The chain is, in some sense, what cosmology can do. From a few well-measured facts and a well-tested theory, we can extend our understanding into the deep future. The understanding is, of course, partial. There are uncertainties in the timing. There are uncertainties in the details of how the merger unfolds. There are uncertainties about what happens to any individual star within the merger. But the broad story is set. The broad story is, in some sense, what we have come to know. We sit, in our particular slice of cosmic time, watching the approach. The cosmic clock ticks, the galaxies move, the future develops. This is what we have walked through tonight. We have walked through M31. We have walked through the distance. We have walked through the trajectory. We have walked through the merger and its consequences. We have walked through the timing. We have walked through the philosophy of seeing into the deep future. We have not, of course, walked through everything. The cosmos is vast. The story of our galaxy is, in many ways, far longer than any single evening's walking can encompass. There are details we did not cover. There are implications we did not fully explore. But we have walked through the central facts. The merger is coming. The merger is far in the future. The merger will produce a single new galaxy. The new galaxy will, in turn, age and fade over many billions of years. This is the long story. We have told a piece of it. Stay with me here. Let me also walk briefly through what M31 looked like at various points in the past, because the deep time history of the galaxy is itself interesting. M31, like the Milky Way, was assembled over cosmic time. Both galaxies formed in the early universe from gas that gathered into dark matter halos. The original dark matter structures formed roughly 100 million years after the Big Bang. The gas falling into these structures began to form stars within the first billion years. By 2 billion years after the Big Bang, the proto-M31 had assembled enough mass to be recognizable as a forming spiral galaxy. The disk had begun to organize. Stars had begun to form in significant numbers. The central bulge was developing. Over the subsequent billion years, M31 grew rapidly by accreting smaller galaxies and gas-rich systems. The growth was, in some sense, hierarchical. Many smaller building blocks combined to make the larger galaxy. By the time the universe was roughly 5 billion years old, M31 had reached approximately its current size. The disk was rotating, the bulge was set, the supermassive black hole was in place. Subsequent evolution involved fewer major mergers, but continued slower growth. During the last several billion years, M31 has been relatively quiet. Some minor mergers with small satellites have occurred. The streams from these mergers are visible in modern surveys. But no major mergers have happened recently. The next major merger, 4.5 billion years from now, will be with the Milky Way. It will be the first major merger M31 has had in many billions of years. It will, in some sense, conclude the relatively quiet phase of M31's history. This is the broad arc. M31 has been there for roughly the same duration as our own galaxy. It has had its own history. It is, in some sense, our cosmic cousin. The merger that is approaching is, in this sense, a meeting between two old neighbours. Each has its own long history. Each has its own structure. Each will, after the merger, become part of a new single galaxy. The distance, 2.5 million light-years, is not vast by cosmic standards. It is, by cosmic standards, intimate. M31 is one of the closest large galaxies to us. M31 is gravitationally bound to us. M31 is, in some real sense, our partner. Most galaxies in the universe do not have such close partners. Most galaxies sit in relative isolation. Our local group, with its two major members and dozens of smaller satellites, is a relatively crowded environment. Let me hold what this means in terms of cosmic statistics. The typical distance between large spiral galaxies in the universe is on the order of 10 to 15 million light-years. Most large galaxies are this far from their nearest large neighbour. Our local group is unusual in having two large galaxies within 2.5 million light-years. This is roughly 4 to 6 times closer than the typical separation. The closeness is one of the reasons that a merger is in our future. Most galaxies do not merge with their nearest large neighbour because the distance is too great for gravity to overcome the cosmic expansion. Our position is, in this sense, special. We are bound to a partner. The partner is close. The merger will happen. Other galaxies in less crowded environments will not merge with their neighbours. They will drift apart over cosmic time. Their fate will be different from ours. The local group is, in this sense, a relatively rare configuration. We are in a small, densely populated cluster of galaxies embedded in the broader cosmic web. The crowding produced the eventual merger that we anticipate. This is what our cosmic position is. We are not alone in our local neighbourhood. We have a partner. The partner is approaching. The encounter will happen. We are crowded. We are bound. We are dancing. The dance leads to a merger. The merger leads to a new galaxy. The new galaxy is, in some sense, our cosmic destiny. This is where we are heading. Tonight, we have walked through the approach. We have walked through the distance. We have walked through the trajectory. We have walked through what the merge will mean. We have walked through the timescales involved. 4.5 billion years to the first close passage. 6 to 7 billion years to full coalescence. Tens of billions of years for the merger product to age into a quiet elliptical. We have walked through the dynamics, gravitational forces, tidal disruption, stellar rearrangement, dark matter merging, black hole coalescence, gas consumption and starbursts. We have walked through the broader context. Galaxy mergers in cosmic history, the local group and its structure, the Laniakea supercluster, the cosmic web. We have walked through the philosophy of all of this, our place as observers, our ability to anticipate the deep future, the cumulative work of generations of astronomers. The picture is, by now, reasonably complete. We have a sense of where we are and where we are going. The understanding is partial, of course. It always is. But it is in some sense enough. We have not, of course, walked through the merger itself. The merger is far in the future. We will not see it. We will only see its preliminaries. But we have anticipated it. We have understood, in the best way we can with current data and theory, what will happen. The understanding is, in some sense, a gift. We can see the cosmic future of our galactic environment. We can see past the limits of our own time by careful application of physics. This is one of the textures of modern cosmology. We see further than our own lives allow. We anticipate further than our own civilization will reach. We understand, in some sense, the deep arc. Let me hold this for a moment. The deep arc of our galaxy includes events on timescales that vastly exceed any human reference. 4.5 billion years to the first merger passage, 7 billion years to full coalescence, tens of billions of years for the merger product to age into a quiet elliptical, hundreds of billions of years for the elliptical to fade beyond recognition. These timescales are not in any way comparable to human timescales. A human lifespan is roughly 80 years. Civilization, in any recognizable form, has lasted perhaps 10,000 years. The species, perhaps 200,000 years. The genus, a few million. The cosmic events we have been walking through tonight occur on timescales of billions to hundreds of billions of years. They are slow on every scale we can imagine. Yet we can think about them. We can model them. We can anticipate them. The understanding extends through the abstraction of physics, far beyond what our biological lifetimes allow us to directly experience. This is, in some sense, the achievement of the human cognitive enterprise. We are not limited in our understanding to what we can directly see. We can extrapolate. We can model. We can deduce. The deduction tells us that M31 is approaching. The deduction tells us that the merger will happen. The deduction tells us, in significant detail, what the merger will look like and what its aftermath will be. The deduction is reliable to the extent that our physical theories are reliable. Gravity, in particular, is one of the best tested theories we have. Newton's gravity, refined by Einstein, has been verified across many independent observations. The predictions for the M31 merger rest on this well-tested theory. The merger is, in this sense, one of the most secure predictions we have about the future. It is more reliable in some ways than predictions about much shorter-term events on Earth. Let me hold the reliability of gravitational predictions a moment. Newton's law of universal gravitation, first published in 1687, has been verified across many independent observations. The planets of our solar system follow Newton's law to extraordinary precision. The orbits of stars in our galaxy follow it. The dynamics of galaxy clusters follow it. Einstein's general relativity, published in 1915, refined Newton's law with corrections that matter at high precision or near strong gravity. The corrections have been tested in many ways, including precision tests with binary pulsars, gravitational redshift measurements, gravitational lensing, and most recently, the direct detection of gravitational waves from merging black holes. The theory is, by current evidence, one of the most reliable theories in all of physics. The predictions for galaxy dynamics follow from the theory with high confidence. The predictions for the M31 merger rest on this confidence. So when we say that the merger will happen, we are not speculating. We are extending the known physics into the future. The extension is, by every available test, reliable. This is what makes the merger prediction one of the most secure things we know about the deep future of our cosmic environment. The science is solid. The conclusions follow. Earth's weather, climate, biology, political history. These are all subject to many complex influences that resist precise prediction. Galactic dynamics, by contrast, follows a relatively simple law that we can solve with confidence. So we know the merger is coming. We know the timing, approximately. We know the outcome, in broad terms. We have, in some sense, taken the deep future of our galactic environment into our intellectual possession. This is what we have done. That, in some sense, is enough. The deep arc for our galaxy leads to merger. The merger leads to an elliptical. The elliptical will eventually fade. This is the long story. Let me hold this longer arc. The cosmic timescales we are discussing exceed everything in human history. The merger, full coalescence, settling into elliptical state, aging and dimming. These processes unfold over tens to hundreds of billions of years. They make the current age of the universe, 13.8 billion years, seem brief. Yet these are the natural timescales for galactic evolution. Galaxies are slow. They evolve at the pace that gravity allows. The pace is patient. By contrast, our own situation is brief. Human history is a few thousand years. Our scientific civilization is a few centuries. Modern cosmology is a single century. Our observations of M31's proper motion are a couple of decades. We are embedded in the long arc, but we see only a small slice of it. The slice is enough to allow us to understand the larger picture, through models and extrapolation. But the slice itself is small. We do, however, have the broad story. We have, in our books and our simulations and our discussions, the description of how the merger unfolds and what comes after. The description is not complete in every detail, but it is complete enough to be useful. This is what we know. This is what we have built up. This is what we add to the cumulative human understanding of where we are and where we are heading. We are at the early evening of it. The galaxy approaches. The light from M31 reaches us, having travelled 2.5 million years. The galaxy is closer now than the light shows. The closing continues slowly, steadily, across the long cosmic timescale. We watch. We measure. We model. The work continues. Let me hold one more aspect. The merger of two galaxies of this size is, in some sense, an event of significant cosmic consequence. The merger product will be one of the larger galaxies in our cosmic neighbourhood. Its central black hole will be one of the more massive in the local universe. After the merger, the new galaxy will be more massive than either parent. It will dominate the local group, gravitationally. The smaller satellite galaxies, if they survive the merger process, will orbit the new product. Over very long times, the merger product will absorb the remaining satellites as well. The local group, currently a system of two dominant galaxies plus many smaller ones, will become a system of one galaxy with a halo of orbiting remnants. Eventually, the remnants too will be absorbed. The end state, in tens of billions of years, is a single large elliptical galaxy with a single central supermassive black hole, surrounded by a vast dark matter halo, sitting in cosmic isolation. This is the long-term cosmic fate. The local group condenses into a single galaxy. The galaxy ages, the galaxy fades, the stars within it gradually exhaust their fuel. New star formation ceases. The galaxy becomes redder and dimmer over many billions of years. In the deep future, the galaxy will be a quiet old elliptical, with its constituent stars slowly dying. The black hole at the centre will, over time, accrete what little gas remains in the galaxy. The accretion will, eventually, slow to a trickle. The end state is a quiet, vast sphere of aging stars and a central supermassive black hole, sitting alone in its corner of the universe. This is what the merger leads to. This is the long arc. We are at the early part of the story. The first close passage is 4.5 billion years away. The full merger is 6 to 7 billion years away. The settling into elliptical state takes another billion years or so. The aging and dimming takes tens of billions more. We have, in some sense, plenty of time before any of this matters, in any practical sense. Hold this last image. M31 sits in our autumn sky, faint to the naked eye, a soft smear of light that is in fact 1 trillion stars. The trillion stars are bound by gravity, organised in a great spiral disk, slowly rotating, slowly falling toward us. We are watching them approach. We will not be here when they arrive. But we know they are coming. We have measured. We have modelled. We have understood. Let me hold one final thought. The understanding we have built up about M31 and the upcoming merger is the cumulative work of many hands over a century. Hubble's distance measurement in 1923, Slipher's velocity measurement before that, the Sohn proper motion measurement in 2012, the Gaia refinements in 2021, the many simulations done by various groups over the past several decades. Each of these contributions is small in itself. Cumulatively, they are substantial. They have given us a detailed quantitative picture of where our galaxy is heading. This is what science does when it works well. It accumulates understanding across generations. Each generation builds on the previous. The cumulative picture, over time, becomes increasingly detailed and increasingly reliable. We are the beneficiaries of all this accumulated work. We did not individually contribute the bulk of what we know. We have inherited it from the work of many predecessors. Future generations, in turn, will inherit from us with our small contributions added to the cumulative store. This is the long pattern of human inquiry. Slow, cumulative, generational. Producing over time an understanding that no individual could have produced alone. The merger of M31 and the Milky Way is one of the things we have come to understand through this long pattern. We have in some sense made the deep future of our galaxy a part of our cumulative human knowledge. The merger is coming. We know the broad story, the narrative is in our books and our simulations and our discussions. That, in some sense, is enough for tonight. Thank you for staying with me through this story.